All right, so this is the secure coding class. There's going to be a workshop at DEF CON for sure and other places. Good. I see Shu has a good example of another product, Unify. Yep, running incredibly old stuff. Yes, there's the problem with these little box appliances. How do you know that the stuff is up to date? That's why the government is pushing for software bill of materials, so you will know. It's not clear how much good that's going to do or how practical it is to do it, but it certainly is not a bad description. Anyway, what we're going to do in this class is set up some insecure stuff and then patch it, which is the step that's missing in all my other classes. And that's why you do need to have some experience coding to succeed in this class. If you are not familiar with how to write any coding in any language, then you'll probably have a hard time. We're going to patch a lot of languages, and you might not know the details of that particular language, but you should know what variables are, what subroutines are, and a general idea how you might patch things. So I'll have a bit of brief lectures each day. I found a pretty good textbook, Designing Secure Software. We're going to cover several chapters out of this book, and the main heart of it, of course, is the hands-on projects, which are down here. And we're going to set up vulnerable systems and patch them, starting with a Linux server. You do need to have a cloud server because it's going to test your patched software from the cloud, from my server. And if your server's on a private network, you won't be able to pass those tests unless you configure port forwarding your router and use a public address on your home network. That would be an alternative to using a cloud server. Anyway, let me start talking about the first chapter here. Now, there's a couple of things that were not in this chapter that I thought I better cover, so I added them just before the start of this chapter, which is, of course, the fundamental idea of what vulnerabilities are. So the Microsoft Stride model is a popular way. Let me try and make this thing the right size. Okay. The Stride model is a way to sort attacks by the type of attack, a common way people look at things. So spoofing is where you pretend to be someone other than yourself, like you pretend to be the administrator or another user. Tampering is modifying things that you're not authorized to modify. Repudiation is doing something and then denying that you did it because you somehow managed to erase the logs and other traces of what you did. Information disclosure is, of course, obtaining information you're not, confidential information you're not supposed to access. Denial of service is causing the service to become unavailable to authorized users by exhausting all the CPU or the bandwidth or simply making a process crash. And then elevation of privilege is exceeding your authorization, such as elevating from a normal user up to root or administrator, so you can do things you're not supposed to be able to do. So those are general goals of attackers. And another thing of great importance to us is the CVSS scoring system. This is everywhere in all vulnerability scanners and all security policies and plans and everything, even though it is a seriously limited and flawed system. There are problems with it, but this is currently the best system we have. You rate how dangerous a vulnerability is from 0 to 10. And 9 and 10 is critical, and most companies don't bother looking at anything unless it's at least 7, because you, of course, find more and more things at these low severities, and you have to somehow everybody has far too many vulnerabilities to patch them all. So you try to somehow prioritize them and pick the most important ones to patch. And this is an amazingly complicated system, and it just got revised to make it even more complicated, where they have numeric factors for all these different considerations. And the end result is many people argue. The vendor says it's a 5, but the independent researchers think it should be a 9.5. There's one that we were talking about on Paul's Security Weekly last week, where the vendor said this is a design feature. This is what happened to a load balancing used by AI systems. They designed it so you can start processes on all the servers with no authentication at all. And that is their design goal. So then they said, don't deploy it on a public network. But people do deploy it on a public network, and then anybody can just launch malicious processes on all the machines, and the manufacturer says this is not a vulnerability, it doesn't deserve a CVE at all, I'm never going to patch it, it's software running as designed. Whereas the actual users and administrators say, my God, this is the worst possible vulnerability, people are running malware on my servers, you have to patch it right away. So it's a disputed CVE, so it will never show up in a list. And so like I say, like everything else, there are problems, but this is the standard in the business, and you'll see it as we go through scanning software. So those are things to know about. So secure programming. We're going to talk about how you get bugs, how they're dangerous, talk about go-to fail, a real important Apple vulnerability that demonstrates how a good example of this sort of thing, and then some more considerations about things that can go wrong. So the challenge is something I've been really focusing on in the last few years in my teaching is a human culture problem. Security people are typically focused on a certain area of specialization and a real expert listing off all the top 10 vulnerabilities and the top 20 SANS controls. And then they're typically sarcastic and dismissive and abusive of managers and coders, saying these people are just idiots. That's why they don't do these things that I think they should do. And that doesn't help. The fact is developers have hard jobs. Now, some of them might be idiots, but most of them are probably sincerely good at their job, but their job is not security. Their job is knowing all the intricacies of their language and knowing how to apply corporate rules with it all and many other considerations. So so this is a problem that the communication between the security experts and the coding experts is often unproductive and unsuccessful. And this is an important thing to realize. If you are a security professional, it is not enough to be technically competent. You must also be competent at persuading people who don't want to hear what you're saying. You have to figure out how to be effective. Of course, nobody wants to hear what you have to say, because what you have to say is usually your product is unsafe and you have to put a whole bunch of work and money and effort into changing it to make it safer. Now, nobody wants to hear that, obviously. So you have to be effective at persuading people to change their ways. Instead of just hostile, you have to be convincing and helpful and encouraging to improve things. Anyway, and of course, software is fragile. So your professional developers, they know how to write code and they know how to test and debug code to make sure that it accomplishes the goal. But they don't really understand security typically. So they make code where when it gets the expected inputs, it produces the expected outputs, but they don't consider malicious inputs because they're not penetration testers. They haven't been trained that way. So the design is perhaps secure. Another problem is when it's actually implemented on real servers, there are changes made, and often it's the implementation that leads to a vulnerability, not the actual design of the code. All right, so the most common problem, however, by far, is untrusted inputs. You have inputs that came from the end user or from another process or another service, and they might be unexpected, and therefore they might influence code. And one thing that can happen is they can send in an attack string which avoids rejection and propagates deeply into the system. That's called tainting, like poisoning water. It now flows through your software with this undesirable input leaking around doing bad things. All right, all software has bugs. You will never get rid of all the bugs. I've often told my students, when you put on patches, all you do is you trade the old bugs for new bugs. So it's a problem. Now, not all bugs are vulnerabilities. Vulnerabilities are bugs that let the attackers come in and harm things. All right, so you can also, when you're rating bugs on something like the CVSS system, it's not necessarily true that if something is a 3, you can ignore it. There can be several 3s that combine to be a 10. And this is something pen testers know. You can combine several minor bugs. So here's an example from a textbook. Developers noticed that if you have orders that come in without a valid warehouse ID, they lead to automatic refunds, and the orders are sent to another warehouse and fulfilled. So that's bad. The customer would get their money back, and they would still get the product. But their customer has no way to change the warehouse ID. That's added by some kind of automatic process, so they regarded this as a low-severity bug and didn't patch it. But then a new change put the warehouse ID in an editable field on the order form. So if the customer changed it, then they'll trigger this and end up getting a free product and a refund. So these 2 small bugs, but the order should be rejected if they change it. So these 2 bugs, which in themselves seem to be minor problems, combine to make a major problem. And that sort of thing happens all the time. All right, so here's another one. You know you have to reboot your phone. I have to reboot my phone every couple of weeks or a month. The apps just stop working and things freeze up. So there are errors, and the errors cause some kind of corruption in the memory of the phone, and they accumulate until it's getting in the way. So That's a thing to know about. So also the errors are common in the easy part of the code. A thing to be aware of, it's the part of code you're not paying too much attention to that looks simple, where you're likely to overlook something simple. So let's talk about go-to-fail. This was a Apple vulnerability from 2014. And here's the actual piece of source code that caused this. This is the HTTPS certificate signature verification, something I'm talking about a lot in the mobile app hacking class. A lot of mobile apps on Android and iPhones fail to validate SSL certificates. And this is one of those vulnerabilities that I was talking about right at the start, where you can have this error in your code and you will not notice because the customer is happy, the websites load, the traffic goes through under normal conditions, so you won't regard it as a problem. It'll pass all your functionality tests, but it's open to hackers who can get in with a fake certificate, which is something your functionality test probably isn't testing. So they're testing various things to see if it's wrong with the certificate. So they check for an error here and load this error message with the result. The idea is if error is 0, then you have no error. If error is some other number, then it's going to pass this number back. So here it checks for something and assigns error to it. Here it checks for something else and assigns error. Here it does the final check for a SHA-1 hash and assigns error to it. And then at the end, it returns that error. The problem is there are 2 go-to-fail statements here. So it's going to consider this, and if this test fails, it will go to the end. But if it passes, it'll do this test. But if this test fails, it will go to fail, and if this test passes, it will go to fail, so it never executes this code. This code here is dead code, which ought to be detected, for example, by your compiler or something, but apparently not. This code can never be reached because, and the fundamental problem is, I think the indentation is the problem. See, this is C. And in C, white space does not matter. You can indent things and put in tabs and carriage returns all you like. There's no enforcement of the layout. So it's not obvious to the developer. What's going on here is if this condition is true, it will execute this command. But if the condition is false, it will execute that command. So this really ought to be indented to the left here. And then it would be easier to see that the thing after it is dead code because both branches of the if skip this. And that means you never do the important test. All right. So if you'd had a language like Python that enforces indentation, it would have made this easier to see. All right. And that was a pretty serious vulnerability. All right. So I guess we'll talk later about the fixes. All right. So here's another one. This happened to me actually just a couple weeks ago. I was in class and students were doing a CTF and it was telling them you got the answer wrong. And I said, oh, I forgot to put the answer in the file. So no answer would be right. And I had an error message in my code that was supposed to pop up to tell you that, but it didn't work because I made this mistake. If you want to see if x equals 8, the correct way to do it in Python is if x equals 8. I think it was PHP in my case, but it's the same. But if you do this, if x equals 8, what this does is it assigns 8 to the value x and then considers the result true. It's perfectly valid, but it is not an if statement in the sense of this at all. So I was missing the double equal sign. It was a single equal, and therefore the thing would never trigger. So that's another mistake you can easily make. And there's a lot of these. It's inhuman to expect developers never to make mistakes like this. So here's some lessons. A small slip can have a devastating effect, and you're not going to catch it if the vulnerable code still works correctly under normal conditions, because that's functionality testing. So code reviews would help a lot. And it seems like a reviewer would have noticed the 2 go-to fails right next to each other, but or even some kind of automated testing. So here's some countermeasures. Test each of the if statements. This is what I should have done in my code. Make sure you test for every if condition to make sure it does the expected thing when it's true and the expected thing when it's false. That would seem reasonable. Watch out for unreachable code, dead code. There never should be any code that can't run at all. That would be pretty clearly. Here's another comment I did, like if Python found the error. But Python didn't find it for me. All right. So make your code flow explicit. If there were parentheses and curly braces around things, it would be easier to tell what's going on. I noticed that. I always avoid this. where you have an if and then one statement. You didn't put curly braces around it because you don't have to, but it would be more clear if you did. And I know when I started writing Node.js, I really got very strict with indentation and curly braces because otherwise you lose control really fast. All right, there's source code analysis tools. We're going to run some of them. You'll see, unfortunately, the free ones aren't that great. And you can have filters. And anyway, measure and require full test coverage would be a good idea. Make sure your tests really consider every condition. All right, and somebody wrote a strong about the go-to fail. I don't think I'll play it, but I put a link in the main page. All right, so here's some vulnerabilities. Atomicity is what causes race conditions, where you have something that takes place in stages. You do step 1 and then step 2, and there's a time delay between step 1 and step 2, and in that time delay, something else can move in and make a difference because you have a multi-threaded processor that's doing many things at the same time. So to avoid that, you want atomicity. Atomicity means you make sure your operation is done all in one step. It either succeeds or fails, but there is no time period when it's only half done. All right. This reminds me of something I saw in cryptocurrency. It's in the cryptography class. There's a blockchain system called multi-chain, and it supports atomic transactions, where you're trying to buy something from me, and in other systems, I would transfer the thing to you, and then your transfer of money to me would come later, and that might not happen. This one, there's a single motion. The object, the ownership goes from me to you, and the money goes from you to me, all as one atomic transaction. And that either completely succeeds or completely fails, and that's what you want. So you don't end up with the product on the wrong side, where I get both the product and the money, or you get both the product and the money. That's atomicity. So in Python, you would use this thing to make a temporary file to store data. You run this function, and it'll give you a temporary file guaranteed not to exist. But the problem is, another process, this will give you the name of a file, but it doesn't actually create the file until you write to it. So one process could ask for the name of a temp file to use, get the name, but before it writes, another process runs the function and gets the same name. Then the other process will write to it, and when you try to write to it, it'll be locked. When you try to read it, you'll get the data the other process put there, that sort of thing. So there's now a better function here, which is an atomic operation, where it creates the file and immediately opens it, creates it right away, so nobody else will get it, which is what should have happened all along. And this stuff keeps happening because, again, it'll pass a functionality test. You try the code, it allocates the file and creates it, and under normal test conditions, you don't have a huge load with hundreds of users all using the system, so it's not likely that some other process is going to also make a file at the same time, so under your test conditions, it'll work. Even when deployed in the field, it'll work most of the time, except under periods of very heavy load, there'll be a small number of errors, and this is why you get these problems where there are non-reproducible random errors. Anyway, so that's timing attacks. Here's another one. We just had a whole bunch of news about this lately. If you can measure how much time it takes to do a cryptographic operation, and the time depends on a secret, then you get information about a secret. The simplest case is if you're trying to do something like multiply by a key. Well, if you go through the key, it's just a bunch of ones and zeros. So you take one digit. If the digit is 0, you don't have to do anything. If it's 1, you have to add something to a running total. So it'll take longer to process a 1 than to process a 0. So a key that is mostly zeros will go fast. A key that is mostly ones will go slow. So you can get some information about how many ones there are on the key by how long it takes. And there are far more sophisticated ones. So, all right, there were meltdown and Spectre related to speculative execution. I'm not sure they're exactly timing attacks, but anyway, there's a new one too that is absolutely a timing attack. Anyway, they have to do with caches. Anyway, the point results. The point is the same. In order to improve performance, modern processors race ahead, performing instructions in advance. So if you go to an if statement that says, if you're authorized to do this highly secure thing, go here, otherwise you have to go there, it's already executed several of those instructions that you're going to turn out not to have been authorized to do. And it will have left behind information in the cache, so you can do cache probing to find out what was put in the cache, so you're able to actually look past the security boundary you're not supposed to be able to cross, and that leaks out secret keys. All right. Ways to prevent this are to reduce the time differential between different operations to an imperceptible level by writing constant time code. And another one is to add an artificial delay to blur the timing signal. Those are possible responses to timing side channels. Anyway, so serialization has led to a whole lot of huge vulnerabilities, where you have some kind of data you're trying to move to the other end, and you don't want to move it in its original format for some reason, so you combine it into some blob. You could combine it with something like base64 or otherwise. One common form is Java Web Tokens. You have a bunch of data that's combined together. The problem is, if you have some kind of security barrier that wants to read this stuff to see if it's malicious, it can't recognize it in the serialized form, so you can sneak bad things through. Pickle is Python serialization. It can be tricked into doing this. Now, the mitigation, of course, is when you serialize it, you put some kind of message authentication code or digital signature so it can't be forged. But the early versions of these serialization platforms didn't have that, so a malicious attacker could just add malicious serialized code. And here's what Java Web Tokens are an example of this. What you're trying to do is send data like this: the type of algorithm, the payload, which includes name and some kind of number, and then some kind of signature. Trying to pass this information, so you combine it and you base64 it, and that's what a Java Web Token is. And if you don't have the signature, then anybody can change this maliciously. You can change yourself to a different user or the administrator or something. Now, that's serialization. There's a lot of vulnerabilities there. All right, so these are things we're going to talk about in later chapters: integer vulnerabilities, floating point vulnerabilities, buffer overflow, input validation, character strings, injection, and web security. We'll talk about these in later lectures, although we're going to start doing them in the projects right away. So let's try a Kahoot. I don't know why I'm suddenly having these coughs, but it happened to a newscaster this week. Maybe there's some new form of a cold going around that gives you this or something. Anyway. Oh no, I think it's Java Web Token. But maybe I'm wrong. Let me just check. Oh, it is JSON Web Token. You're right. Thank you. Good. I didn't know that. All right. Good. All right, let's try this. That makes more sense, actually. All right, so what will this C code print when x equals 1? Well, I was surprised. Perhaps people, unfortunately, the code is no longer visible, but the very first statement was if x equals 1, go to fail. That'll be true, and it'll go to fail. Just print 1. There was nothing wrong with that code. Now, there was 2 go to fails later on, but the very first if condition was true. All right. I can see in the future I'm going to have a screenshot I have of the picture. Anyway, the right answer is 1, which nobody got. All right. All right. What will prevent brace conditions? That's atomicity, right? Doing things in one step so there is no condition where it's partially done and vulnerable. All right. Which one may reveal malicious code and execute it? Deserialization. When you serialize something, you take a bunch of data and roll it into a blob, and it's when you unpack it that you might reveal hidden malicious code and execute it. The deserialization is where it happens. All right, let me record the winners here, and then I'll go back and talk about that one everybody got wrong. All right. Now, I think that one was straight from the slides. So if I go back in the slides, we can see it. Oh, yeah, mine was a little simpler. Let me just run that Kahoot again. All right, I'm going to just start it again so we can see it. Don't need any players. Well, maybe it won't go without any players. Very annoying. All right, I'm going to do it another way. All right, let me get something here. I've got those things here. All right, I'm going to get the code. There we go. Here's the question. All right. There we go. There's the question. So what's going on here is x is 1. The first statement, if x equals 1, go to end. So this is true. So it goes down here and prints x. That's it. It never executes any of this code if x equals 1. Now the interesting conditions are, now if x equals 2, this condition will be false. So it will go to the next test. This condition will be true, and it will go to end and hit the end. Now, if x equals 3 is when you're going to have a problem. X equals 1 is false, so it goes on to the next one. X equals 2 is false, so it skips this statement and goes to this one, but it skips over this, so it never executes this code. So when x equals 3, it will print a 2 in error. Anyway, that's the essence of go to fail. All right. So, yeah, you could have. All right, anyway, so that's what I wanted to show you. Let me stop this recording if I can figure out where my OBS is. All right.